Thank you so much.
No worries.
Mr.
Yes, Arun?
What are you going to explain section 2?
Can I what?
What are you going to explain?
What am I going to explain?
Yes.
You will see that in a minute. I'll
Yeah,
start-
Mr. I want a question in the sample problem, how you know it's negative or positive?
Oh yeah, you look at the temperatures to know if it's negative or positive. If, for example, if the temperature for the water is given, you look at the temperature for the water, the initial temperature and the final temperature. See if it's increasing or it's decreasing. If it is increasing, like initial temperature is lower than final temperature, then it means that this water is increasing temperature. The final temperature is bigger. It means it's gaining energy. It means it's positive. The Q is positive. Or if it's the opposite, then it means it's negative, because then the initial temperature is high, the final temperature is low. It means it's losing energy. It means it's cooling down, which means the value will be negative. Look at the video, Ranu. I'm sure you will understand. The video that I posted on YouTube. I'm sure you will understand that.
Hello, Mr.
Hello, Dina. Yes.
Mr.
Yes, Naz?
Can I ask a question?
Yes, sure.
In Dale لرجعنا بسرعة كرد, how can you change object from state to state?
An object from a state to state.
Okay. Yeah, we wrote 2 points. So I can't remember them.
Ah, yeah, you mean, yeah, the states of matter. But that was not in this chapter, by the way, Naz.
No, it was in this chapter.
So
It was in section 2.
in chapter 2, I remember we studied you can change the states of matter from solid to liquid and liquid to gas by changing thermal temperature and mechanical temperature. But that was on chapter 2, if that's what you're saying.
Like one point of them was a specific heat capacity.
Ah, yeah, now I understand what you're saying.
And
So yeah,
another.
yeah, I understand what you're saying, Nas. So the question is for this one is, a material is changing its temperature by 2 factors. 2 things will make a material change its temperature: the external force, like the external energy it's gaining, and also its specific heat. So, like for example, I'm under the sunlight, my temperature is changing. I'm feeling hot. What causes that? 2 things cause that. First, the sunlight, the external source of energy that I'm receiving, how hot the sun is. Is this a summer sun or is this a winter sun? All right, so this affects my temperature change. The second thing that will affect my temperature change is the specific heat of my body, the particles that I'm making in my body. How are their specific heat? Is the specific heat big or low? If the specific heat is high, then that means I'm resisting temperature change. If the specific heat is low, that means I'm very easily changing my temperature. That was the point, Nas.
Oh, okay. Like the 2 points are the external energy and the specific heat capacity, right?
Yes, that's correct.
Thank you so much.
Welcome. So those 2 things affect the temperature change. Yes, Shanas?
Page 82 and not include.
Page 82 and 83?
Yeah.
Yes, not included except for the section review. The section review of page 83, section review for 1. This is included, but the rest, no.
Yeah, thank you.
Okay, so how about we move on to chapter 2 right away? No, not chapter 2, sorry. Chapter 4, section 2. So chapter 4, section 2, specific heat. We start with the idea for specific heat. I think now that Nas asked the question, we explained the upper part of this page, in which we said when you are changing the temperature of an object, specific heat has a role in it. Like some materials, they change their temperature very easily. Some materials, no, they do not change their temperature very easily. And this is because of specific heat. Each material, each different element has a different specific heat. So they respond to change in temperature differently. If specific heat is high, then that means, this object is not changing temperature very easily. The higher the specific heat, the more difficult the temperature change. Why I cannot see myself on the screen, by the way? It's kind of weird. This is the first, oh yeah, there we are. Let me see, gallery. Oh yeah. Okay, so yeah. Specific heat basically tells you how resistant are you to temperature change. It's the amount of energy. This is the definition on page 84 on the left side, lower corner. You have the definition for specific heat. It says it is the quantity of energy that is needed to change the temperature of a substance by 1 degree Celsius if the substance is 1 kilogram. This is the definition. So specific heat, you have two definitions actually. This is one of it. And then the other definition, which is again for specific heat, it says the same thing, but it is only expressed differently, which is in the middle of the page. The specific heat is highlighted and it's bold black written. So it says the amount of energy that is added or removed, to each substance. So the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. This is what the definition says. So you could memorize any of those two definitions, either the one in the middle, or you could go for the one on the left. Both of them are correct.
Mr. Just a question.
Yes, Parisa.
Mr. Practice 4A on page 83, is it included?
No, it's not.
What about the section review?
The section review, yes. Not the practice, but the section review, yes.
Okay, thank you.
All right. So yeah, that was specific heat. In specific heat, the equation, 3 things you must mention. 3 things, 3 keywords. The energy needed, the mass for the material, and the temperature change for the material. 3 important variables we have in specific heat. So I'll write down all the 3 for you and put it in an equation. This is specific heat, Cp. The energy required, heat, or Q as a symbol. The mass for the substance, M. And delta T, change in temperature.
For which page?
This is page 84.
Okay.
Okay, so on page 84, you have specific heat here. Actually, let me write down all the things here. This is specific heat. This Q is heat required, the amount of heat that is required. And then this M here is the mass, which is usually 1 kilogram. Like the standard is 1 kilogram. It doesn't necessarily mean in the questions we will have 1 kilogram. I could give any kilograms I want, but the standard for the definition is 1 kilogram. And then delta T is change in temperature. And it's usually 1 degree Celsius as a standard. You could say 1 degree Kelvin, or 1 degree Celsius. Both will be correct, doesn't matter. You can even say 1 degree Fahrenheit if you want, as long as it's 1 degree change. Yeah, so this is the equation for specific heat. Please do know the equation. Like, I know there's no question to find specific heat on the book. So far we've studied, even the sample problem, you don't find specific heat. In the sample problem, you find, I think, initial temperature, yeah. So you don't find specific heat, but we did find specific heat daily. I created an equation, like a problem, and we solved specific heat on daily. I gave you Q, I gave you M, and I gave you delta T, and we found specific heat. I think we did a practice on that. So yeah, I could be giving you heat, M, and delta T, you find specific heat for me. Or I could give you specific heat, M and delta T, and tell you to find Q for me. That I can do as well. Or I can give you specific heat, Q, and mass, and I tell you find delta T for me. So I could give any of those three and tell you to find the other for me. Very easy. You just rearrange the equation. How do you rearrange the equation if Q is unknown? What will happen to the equation?
Let's take it to other side. It will be CP multiply mass multiply delta T.
Very good. So if Q is unknown, you will have CP times mass times change in temperature. So CP is basically specific heat times M, which is mass, times delta T, which is the change in temperature. This way you're finding Q. So I could be giving you those three, and I ask you find Q for me. Or I could do the opposite, right? I could tell you find mass for me. If you find mass, what do? You switch places with that. Just switch those two. If I tell you find delta T for me, again, you will switch places with the CP. But if I tell you find the Q for me in the numerator, then you multiply. As for the denominator, you just switch places, very easy. Yeah, so this is it. For page 84, that would be it. And one more thing for page 84 is the sign for Q. Q is not always positive. It could be negative. The amount of heat that is added or removed. If it is added, yes, it is positive. But sometimes in some problems, the heat is removed. The amount of energy is removed. In this case, your Q will become a negative value. So it could be positive, it could be negative, depending on the situation. If your temperature is increasing, then that means it will be positive. If your temperature is decreasing, then that means the Q is negative. So it depends on that. It depends on the delta T. And delta T basically means T final minus T initial, right? Sorry, let me pick this better. So yeah, T final minus T initial. This is delta T. So if T final is bigger, then the value will become positive. But if the T initial is bigger, then the negative sign will win over the positive sign here. So then your value will become negative. The delta T will become negative. And if delta T is negative, your Q will be negative. If delta T is positive, your Q will be positive. This is it. So it all depends on the T initial and the T final. Which one is bigger? If the T final is bigger, it means you're gaining energy. It means your Q is positive, and vice versa. Any questions? So let me actually give you a couple problems here. A material has initial of 20 degrees Celsius. But eventually, oops, this is capital, but eventually increases temperature and becomes 25 degrees Celsius. So in this case, you have a material, the initial temperature for the material is 20 degrees Celsius, but the final temperature is 25 degrees Celsius. Now, if we have the equation, the delta T, how do I put those values back in? Only into delta T. Not
You
like
write
I'm not solving the whole.
T
Yes,
minus TI.
you will write
TF
down
minus TI.
T final, yes, minus T initial. Now the T final
T
here
initial.
is how much? T final
20.
20
It's 5.
25, yes. Minus the initial temperature is
20.
20. And when you subtract them, you will get
5.
5 degrees Celsius. Now this value is clearly positive. So the delta T is clearly positive. And what will be the Q? Is the Q positive or negative in this case?
Will be positive.
It will also be positive. The Q will also be positive because this substance is gaining energy. It's increasing temperature. This is the idea for the positive sign and for the negative sign of Q. Yeah, I guess that's it for page 84. Nothing left. For page 85, which is the final page, it's not the final page included, but it's the final page that I will explain, because page 86 is also included. Do not confuse that. Yes?
Delta T was positive, so the Q is positive.
That's correct.
Oh, okay. Thank you.
Okay, so then we have page 85, in which we have a table. This table on the upper part, not important. Do not memorize it. I'll give you the values myself. Then we have determining specific heat. You can determine specific heat for an unknown material. I'll give you material. You don't know what that material heat is, but you can find the specific heat for it. How do you do that? By a procedure which we call it calorimetry, which is on the right side of the book. The definition is there. An experimental procedure used to measure the energy transferred from one substance into another. So if you know the energy transferred from one substance into another, you can put this energy, the Q, into the equations, and you can find specific heat for the unknown material. On page 85, you have the device, the calorimetry device. On page 85 on the right side, this device always contains of two different substances. One of them is fixed at water. One of them is always water. The other one is your unknown substance. Instead of water, you could use any other substance, by the way. You could use gasoline or any other liquid that you want. But water is very well known. Water is something we know the values. We know the specific heat for water very clearly, very specifically. So we use water all the time. And the equation that we use in cases of calorimetry is equalizing two Qs, two equations for Q on left side and on right side. And this is based on the conservation of energy, because the energy that is lost from one object will be gained by another object. This is the idea for conservation of energy as well. So you have two Qs in cases of calorimetry problems, Q1 and Q2, right? They equal to each other. So you equal both sides. And the first Q, it is fixed at water. We always have water as one of them. The other one, it depends on the material. So I'll just call it M, material. The book says X here, but then on the sample problem, it again says M. We could just go for the M. This M stands for the material. You could give it your own subscript. I don't mind it. You could say QS, however you like. But this W is fixed on water. Yeah, so the first thing that you do is you find which one is positive, which one is negative, based on the temperature, the change in temperature. Let's say the water increases temperature, so the water is positive. And the material is losing temperature, decreasing temperature, giving off temperature. So let's say the Q of the material is negative. So once you determine the positive and the negative, write down the whole equation for them. Cp on the side, M delta T equals to Cp on that side, M delta T. Both same equation, except for that we have a negative here. For one of them, you always have a negative. And then you can write down the subscripts. This is W here, another W here, and then another W here. And for this one, you have mass, the M for the material. Sorry, the specific heat for the material, the mass for the material, and the temperature change for the material. Yeah, and one final step is left, which is opening the delta T. Sometimes, like the sample problem, you need to open the delta T eventually. So you'll have Cp mass, and this delta T will become T final minus T initial. T initial is written as TW for water. And this will equal to, again, minus, you don't forget the minus, of course, Cp for the material, the mass for the material, and finally the delta T for the material, which is T final minus T initial for the material, which is Tm. Okay, so you will have everything except for one variable. One unknown will be in these variables. You will isolate it and you find it. It could be the CP, it could be the mass, it could be TF, or it could be TM. Any of those variables could be unknown, but the rest must be given. And you will
So
isolate.
is the CP always negative?
Yes, Darin?
Is the CP always negative?
The CP on the left side or on the right side, because we have two CPs.
Right side.
On the right side.
Right side.
Not necessarily always the right side is negative, Darin. You have to know which substance is losing energy. This will be negative.
Oh,
Okay.
okay. So
So, for example, Darin, on the sample problem on page 86, in this problem, the material is gaining energy. Sorry, not the material, the water is gaining energy. So the water is positive. It doesn't
material is
tell you
negative.
this about the substance, by the way. It doesn't tell you if the substance is losing energy or gaining energy. It only tells you that the water is gaining energy, because first it has 21 degrees Celsius, then it becomes 25 degrees Celsius, which means the water is gaining energy, which means the water is positive. And this automatically tells you that the Q for the material is negative. Once you know one side, you will know the other side. This is how you deal with it. And it could be any of them. In another example, the water could be negative, depending on which one is gaining energy and which one is losing energy. Yes, Shana?
Mr. I think in here, like only the negative and the positive sign is important. Like, is it necessary to write all of these equations to know if the water has gained or lose the, like?
Yeah, well, the whole thing is important, Shana, because on page 86 you have the sample problem in which you have to write down the equations, right? This is what I explained here is page 86.
Okay.
Yeah, so yes, you should know the whole equations because you need it in page 86. And I will not explain the page 86, as I said. I only this is the general form. But for page 86, you could go to the video. Yes, Dina, you have a question?
Yes, Mr. For the this equation, will you bring will you bring it for the exam?
Yeah, why not? The sample problem is included, so yeah, I could bring.
Mr. You will bring the same as the sample problem, or you will change the numbers?
I'll see what I can do. I'll do something. I could change the numbers. I could bring it as it is. So.
But Mr., it's the same idea as the sample problem?
Yes, same idea. Yes, yes. It must be the same idea as the sample problem.
Okay, Mr.
So do understand it, and you will do fine.
Thank you, Mr.
Yes, Suzanne?
Mister, for the third part of the equation, you wrote CPW, but in the other part, why didn't you write negative
Yeah.
CPM?
Yeah, that's out of carelessness. Let me write down the subscripts.
Okay.
Yeah. So yeah, you should write it so you distinguish them. Okay, so this is how it is. And one variable here, sorry, like two variables have the same value from this equation. It doesn't matter if it's on the left. T final. Yes, very good. It doesn't matter if it's on the left side or if it's on the right side. They have the same value. Those two are equal. Both of them will equal to one another. And the reason for that is because of anyone? Why are they equal?
Thermal equilibrium.
Because of thermal
Because
equilibrium.
they're in thermal.
Yes, thermal equilibrium. Because they're in contact, those two materials. Yes, their initial temperature is different, but once you put them in contact, eventually the final temperature will be equal. So the T final is always equal. And this is the same case for page 86, the sample problem. The final temperature is given, which is 25 degrees Celsius. This 25 degrees Celsius goes for the water and also goes for the aluminium. For both TFs, it's both 25 degrees Celsius for the water and for the aluminium. But their initial temperature, no, it's not the same. For the water, it's 21 degrees Celsius, but for the aluminium, we find it. It's on page 87, the final answer. The T initial for material is 81 degrees Celsius. Very, very hot at first, but then it loses energy. It becomes 21 degrees Celsius. 21 degrees Celsius, 25 degrees Celsius finally. So you're going from 81 to 25. This is a lot of change in temperature. And this only tells you how low the specific heat for aluminium is because it's changing temperature very easily. Naz, you have a question?
Mr. in page 86, the sample problem.
Yes.
It didn't give us the CP of water.
The CP for water, yeah, it is not given. I'll give it to you, do not worry.
Okay.
Yeah,
Thank
I think you already know the specific heat for water, 4.1 times 10 to the power 3. You already know it, but I'll give it to you anyways. Yes, Nas, you have a question? Sorry, Dina. Dina, any
Yes,
question?
Mr. The table on page 85, like, show me more, is it?
No, do not. I'll give you the values myself.
Ah, okay, Mr.
Priya, any questions? Priya? No questions, I guess. Alan?
Mr. For the equation,
Yeah.
like if we say the something else is like undefined, we did like, let's say the CP is, we didn't find the CP, so it says to you the equation tells you find CP.
Yes.
Is it the same thing as the YouTube when you send it to us?
Not exactly the same thing, because the rearranging will be different. Like, for example, Alan, if this CP is unknown, let's say that this is unknown. So what do you have to do? You will have to take all those that is next to it to the other side. Okay. What is a multiplication? When you take it to the other side, will go to the denominator. If something is minus, when you take it to the other side, it becomes a plus. So the rearranging will be different. Until here, it's all the same. Until this final equation, it's all the same. But then what is unknown? The rearranging will be different. You have to isolate what is unknown. You have to leave it on one side alone. So rearranging will be different. But for now, because we are only including the sample problem, so only finding T initial is important. The rearranging for T initial, only that would be important. Okay, Alan, like, just stick to the way the sample problem do it.
Okay, thank you.
Now, for next lessons and when we go back to school, we will do the other rearranging as well. Tara, any questions?
Mr. How many multiple choice and how many writing,
I
and
don't
how
know.
is the exam?
I don't know, Tara. No idea.
Why?
I have not said the questions. I'll set the questions after the lesson is over. Okay.
Okay, thank you.
Mr. Can I ask a question?
Yeah, Bria, go ahead.
For the chapter review, there are many questions which are directly related to what we are studying.
Yeah, very good. Yes.
Is it important?
Yeah, it is important.
Like, to study them?
Yes, it is important. And I was thinking to spend the last minutes that we have left on those questions. How many minutes we've got left?
Especially the first 10 to 13 questions.
Exactly.
They're like,
Yeah, exactly.
very
Especially
important.
like very important. Yeah, that's very correct. Especially the 7 first questions, I assume, like very, very related to what we've been studying. How many minutes we've got left, Bria?
I guess 15 minutes, something like that.
15. We can spend those 15 minutes to some of those questions, actually. How about we?
Mr. I have a question.
Yes, Nas.
For the sample problem, page 86, like if tomorrow we'll bring the sample problem, we'll find like T initial.
Yes.
Just the T initial is important.
Yes. Only how do you rearrange the
Okay.
initial? Yes. But like once we go back to school, we will have the practice 4B, and then we will have some questions in which you find T final, some question in which we will find the specific heat. So then we will care about that. But for now, no. Let's just stick to the TM.
Like for tomorrow, just chill.
Yeah. Right.
Okay, thank you.
Okay. Let's see.
But
So
sir,
yeah.
just before going over the chapter review, there's a table in page 103. Shall we memorize these quantities?
103.
Contains, I guess it contains all of the quantities.
The symbols for them. You already know it. No, you do not know. You do not need to go to this table. No, Bria, you already know all of that.
Okay, thanks.
It's all there from the previous ones. Okay, so how about we go to the chapter 4? Like, this is Bria's idea, and I completely agree with him. On chapter 4, we have the chapter review on page 104. I know we have not included page 104, but these are questions, and I could bring questions like this. So this will be a practice. Like, these questions could be on the exam. Why not? I mean, let's solve them. We have 10 minutes left, and let's dedicate those final 10 minutes for those questions.
Only 8 minutes left.
Yes, Ranu?
Only 8 minutes.
Yeah, we could solve a couple of questions in those 8 minutes. Let's start with the first one. This is chapter 4 review on page 104. Question number 1, we have, what is the relationship between temperature and internal energy? Yes, Reena?
Sir, they're directly proportional.
Very good. Directly proportional. This is number 1. Temperature and internal energy are directly proportional. That is correct. Not necessarily in all cases, but mostly yes. So that was number 1. Question number 2, what properties of two objects determine if the two are in thermal equilibrium? Like, what can tell you if two objects are in thermal equilibrium? Yes, yes, Avesta? No, Avesta is trying to join. She was not raising her hand. Let me see. Bria?
Is it their temperature?
Yeah, of course, it's the temperature. That's right. If the temperatures are identical, then this determines if it's in thermal equilibrium or if it's not in thermal equilibrium. Yes, your answer is correct. So what determines if an object is in thermal equilibrium? Temperature determines that. The property of temperature determines that. So temperature determines if your object is in thermal equilibrium or not. If they're identical, yes, it is in thermal equilibrium. If there's a difference, no, it's not thermal equilibrium. So yeah, correct. Good answer. So let's move on to question number 3, in which we have a very beautiful drawing. And so this is the question. Let me read it for you. Which drawing in this figure correctly shows the direction in which the net energy is transferred by heat between an ice cube and a freezer wall when the temperature of both of them is minus 10 degrees Celsius. So we have the freezer wall, and also you have an ice cube. Both of them, the temperature is negative 10, both of them. So how is the energy being transferred? Is it A, the energy being transferred from the ice cube to the wall, or is it B, no energy being transferred? Or is it C, the energy, heat, is being transferred from the wall to the ice cube? Which one is correct? A, B, C. Very, very, like, this is a very reasonable question. I would love to have this question on my exam paper. I'm not sure if I'll be able to do it or not, but this is a very reasonable, I love this question. Let me see.
Mr. Can I?
Yeah, sure.
B, because they have the same temperature.
Very good. Exactly. B, because they have the same temperature. If they have the same temperature, they're in thermal equilibrium and no heat is being transferred. So you don't have heat. This arrow, this red arrow, should not be there. So yeah, your answer is correct. It is indeed B. Question number 3, we have B. This is the correct answer. How about we move on to question number 4. Yeah, a glass of water has a temperature of 8 degrees Celsius. In which situation more energy will be transferred? When the air's temperature is 25 degrees Celsius or 35 degrees Celsius? Very, very easy. You have a glass of water, 8 degrees Celsius. In which situation there will be more energy transferred? If the air around it is 25 degrees Celsius or if it is 35 degrees Celsius? Yes, Rowan?
When the air temperature is 35 degrees Celsius.
How much, Rowan?
When air temperature is 30 degrees Celsius.
Very good. Why? That is correct indeed, but why? Why didn't we choose the 25? Why the 35?
Because it has more energy to be transferred.
Yes, you have more energy difference, right? More energy difference, therefore more heat being transferred. Like for the first case, you have 25 minus 8, right? And you will get 70, the value, like the difference between those two. But for the third one, you have 35 minus 8, which means 27, I guess. So yeah, clearly the 27 is a greater temperature difference, so therefore you will have more heat being transferred. Very reasonable question. Question number 5. How much energy is transferred between a piece of toast and an oven when both are at temperature of 55 degrees Celsius? So you have an oven and then you have a piece of toast in which both of them have 55 degrees Celsius. Both of them very hot. Both of them high in temperature. So it says, how much energy is being transferred? And explain your answer. Let me
Is
see.
it Mr. both of them 25?
Both of them, no, both of them is 55 degrees Celsius, but the amount of heat is being transferred. How much is the amount of energy? Yes, Rina?
Mister, there will be no energy transfer because they have the same temperature, so they're in thermal equilibrium.
Very good. This is indeed the correct answer. Because both of them have 55 degrees Celsius, because both of them are have identical temperatures, therefore they are in thermal equilibrium, therefore there is no heat being transferred. So no energy is being transferred. This is indeed correct. So this is question number 5, in which no heat is transferred. Okay, no heat is transferred, and the explanation is because the objects are in thermal equilibrium. Equilibrium, yeah. Which means if they are in thermal equilibrium, it means they have identical temperatures. Yeah, so this is it. This is question number 5. How many minutes we've got left?
1 minute.
Okay, so please take a picture of that, and so that we end the lesson. And that would be it. Any questions, guys?
No, Mr. Thank you.
Sir,
Yes, Shahnaz.
can you send the important questions of section reviews, the answers, please?
Those 5 ones, Shahnaz. You mean the chapter review?
No, section review.
The section review on which page?
Like both of them, the section reviews.
We have section review on. Yeah, so we only have one section review, Shahnaz, page 83, and that's it. 3 questions, and that's all the section review that we have. We only have one section review, Shahnaz. Nas, any questions? Okay, so no questions. Please take a picture of that, and that would be it. You guys can leave. Have a good time and good luck tomorrow.
Thank you, Mr.
Bye-bye.
Thank you, Mr.
Bye-bye.
Thank you. Bye.
Bye-bye, everyone.
Mr.
Yes.
Mr. For the math problem, like how many math problem you will bring in the exam?
I don't know. I'll set the questions now. As soon as you leave, I'll set the questions.
Okay, Mr.
I'll see you
Thank you. Thank you, Mr. Bye.
Good luck. Bye.
Thank you, Mr. Bye.
Bye-bye. Good luck. What are you waiting for? Mustafa Abdul Samad? Clearly not there. Payman Aya? Probably they're just staring. Yeah.
Set the exam paper.
Yeah, Payman?
And we'll just watch. Set the exam paper and we'll just watch. Yeah.
Yeah, that would be a good idea. But Mustafa is definitely not there. Yeah. Nice view. Okay, guys, bye-bye. I'll see you around. Good luck.